Okay, let's talk about a real-life example of the special theory of relativity. In fact, a classic example showing that it actually works in real life. It's of a particle called a muon. And it is muons are sort of like electrons, but they're much heavier, about 200 times the mass of an electron. They're also short-lived particles. They decay into other things. And so the average muon lifetime is about 2.2 microseconds, 2.2 millionths of a second. When they get created, they can be created in particle accelerators, but they're created naturally when cosmic rays coming in from outer space hit various atomic nuclei, atoms in the atmosphere, and the resulting sort of spray of particles that comes out of it. Some of those particles are muons. And the height at which they are typically created in the atmosphere is about 10 kilometers. So here's our rough diagram here. Cosmic rays coming in. Some of those cosmic rays get all the way down to the surface of the Earth, but some of them will hit atoms in the atmosphere, and out of those collisions, muons will be generated at about a height of 10 kilometers. We know that if the muon is just sitting there at rest, its proper lifetime, note we put proper in here, remember we're talking about proper time. In other words, that its time at rest, it has a little internal clock, you can imagine, not literally, but internal clock, such that it will live for 2.2 microseconds, just sitting there. So that's its proper lifetime. Its lifetime measured in its rest frame, as it were, its frame of reference when it is at rest. Also, average velocity of these muons created is very, very high, 0.998 times the speed of light. Okay, so not quite the speed of light, but very, very close to it. And so given the fact that we know its lifetime, how long it's going to exist before it decays into other particles, just spontaneously in average, and then also its velocity, 0.998 c, you do a little calculation there. It's traveling very fast, but it's not living very long, not existing very long. And so the distance traveled, about 660 meters is what it comes out to be, the speed of light. This essentially being pretty close to the speed of light, 3 times 10 to the 8th meters per second. But 2.2 microseconds is 2.2 times 10 to the minus 6 for those of you who do those sorts of calculations. And so you get on the order of several hundred meters in terms of the distance traveled by an average muon, supposedly, well, not supposedly, but generated by these cosmic rays, supposedly will travel 660 meters. There's a problem here, however, because at the surface of the Earth, 10 kilometers below where these muons are being generated, we see a lot of these muons. So what's going on? Because according to the calculation here, they can only travel on average 600 or so meters, 600, 700, something like that, and yet they have to go 10,000 meters to get down to the surface of the Earth where we observe them. And we know they are created at about a height of 10 kilometers. So what's going on with that? Well, the explanation comes through the special theory of relativity. So let's imagine, first of all, we're outside now, we're observing these muons. We know their proper lifetime is 2.2 microseconds. Okay? But remember, moving clocks run slow. So as I say I'm observing the muon's lifetime, it's in the sense this internal clock ticking away in there, I will see it live longer. Okay, and if you figure out what 0.998 c is in terms of gamma, our gamma factor, gamma being 1 over square root 1 minus v squared over c squared. With this velocity, you'll get, it's about 15, I think, something like that, in that vicinity. So in other words, from our perspective, we will observe the muon's average lifetime increase because its clock will tick more slowly from our perspective as we observe it. In fact, it will tick 15 times more slowly. And therefore, from our perspective, it will be able to travel 15 times longer than this calculation we showed right here. And clearly, 15 times 600 meters is going to give me plenty of distance, plenty of distance for the muon to get down to, well, it'll be fairly close, but 15 times 660 gets you right around to 10,000 meters or so, and so we will see the muons at the surface of the Earth. So it makes sense then. Now you might also ask, though, well, what about from the muon's perspective? Because the muon's perspective, its clock is ticking at 2.2 microseconds in terms of its lifetime. At that point, it goes out of existence. So how do you explain it from that perspective? Well, here's where the other aspect of the special theory of relativity comes in that we've been working on this week, and that is length contraction. So the muon sees its clock just ticking away normally, right? It doesn't know, of course, but we'll say it knows at 2.2 microseconds, okay, lifetime is up, time to decay into something else, give up the ghost, as it were. But how does it then get down to the surface of the Earth? Well, as it's coming down through the atmosphere, it's seeing the surface of the Earth rush up towards it at a speed of 0.998 c. Because remember, as far as this is concerned, it's just sitting there. If you could imagine yourself as an observer, as a rider along with a muon, you'd just be sitting there looking at your little clock, as it were, ticking away up to 2.2 microseconds. You're at rest, but you're seeing the surface of the Earth. In your frame of reference, you're at rest, but you're seeing the surface of the Earth rush up toward you at 0.998 c. And if something is moving toward you at that speed, you have a length contraction effect. And so that contracts the length from 10 kilometers to about 1/15 of that. Actually, sort of around about 600, 600, 650, something like that. And so for the muon sees a length contraction effect that enables it to live only 2.2 microseconds but still get down the surface of the Earth. From the outside observer's perspective, as we're observing the muons, it's traveling the full 10 kilometers, because that's in our frame of reference, but we see it live for a lot longer because of the time dilation effect. So from one perspective, it's the time dilation effect kicking in. From our perspective, from the muon's perspective, in a sense, it's a length contraction effect that enables it to get down to the surface of the Earth. In both cases, it matches up with experiment, as we have to have it. Otherwise, we'd have a contradiction and something would be wrong. We know the muons get down to the surface, and now we can understand that both from the muon perspective, as it were, and also from our perspective. So, very nice real-life example of the special theory of relativity in action.